Hello, people.
Hello, Professor.
Oh, hi there.
Crap, I need to print that out.
All right. Any questions before we begin?
I have question from homework 1.6, the number 9.
1.6, number 9. Let's see. Ooh, all right, that's good. And you did now, computer. There we go. That's the only problem I did from 1.6. Wow. All right. 1.6, number 9. You have the limit as t approaches infinity of the square root of t plus t squared over 3t minus t squared. Okay. So for this one, we do the power trick. What is the highest power of the denominator?
It will be the square.
Good. So first I'm going to rewrite this as t to the 1/2, right?
Okay.
You get t to the 1/2 over t squared plus t squared over t squared over 3t over t squared minus t squared over t squared. Oh, don't forget your limit.
Oh yeah.
And then we reduce. So you'll get the limit as t approaches infinity and 1/2 minus 2. That'll give you, or 2 minus 1/2, that's at 1.5. That'll give you 1 over t to the 3/2 plus 1 over 3 over t minus 1. And now these two share the form of 1 over x to the n. And we know that as the limit of x approaches infinity of 1 over x to the n, this limit will become what number?
0.
0. So that means these two limits become 0. And you get -1 as your answer.
Okay, cool. Thank you, Professor.
Yep. Okay. Well then. Okay, cool. So with that being said, I guess we can jump into 3.1 and 3.2 today, which deal with more limits. Yay. Not really, but yay.
Yay.
Oh, there's Ryan. Hi, Ryan.
I've been here. I called you a nerd.
Oh, I didn't hear that.
You like responded to it.
Yeah, whatever, nerd. Oh yeah, I guess I should upload the notes I'm going over. Let's see. 3.1, 3.2. There it is. Bam. There's the notes for you to follow along. Okay, today's about the limits of exponential functions and logarithms. So we do 3.1 and 3.2 all in one go. All right, so let's get over some limit laws for exponential functions. If the base of an exponential function is greater than 1, then the limit as x approaches infinity of a to the x will equal infinity, or the limit of a to the x as x approaches negative infinity will be 0, as shown by the graph below, right? So if x approaches infinity, your y values head towards infinity, but if x approaches negative infinity, your y values will approach 0. Okay. And then if the base is between 0 and 1, then the limit as x approaches infinity of a to the x will equal 0. And the limit as x approaches negative infinity of a to the x will be infinity. Again, seen by the graph below. So if x approaches infinity, y gets closer to 0. And if x approaches negative infinity, then y heads towards infinity. And these are your limit laws for exponential functions. Okay. And these same rules would apply for the e to the x function. The limit as x approaches infinity of e to the x would go to infinity. And the limit as x approaches negative infinity of e to the x would be 0. Again, shown by the graph. So we will apply these limit laws to the next page. Hang on, got another teacher texting me. All right. Okay, let's go then. Let's try out these limit laws. So number 1, find the limit as x approaches infinity of 2 to the negative x minus 1. Well, if we want to use the limit laws above, this means that we're going to have to rewrite 2 to the negative x. So what is another way to rewrite that?
1 over 2 to the x.
1 over 2 to the x minus 1, right? And then, well, you can rewrite it one more time just to make it look like an exponential base. So 1 over 2 to the x can also be rewritten as 1 over 2 to the x minus 1. They are all equivalent. And now, if you reference your limit laws above, we see that the limit as x approaches infinity of a to the x, with a being a base between 0 and 1, will head towards what number?
0.
0. Good. I'll put that down below, where a is between 0 and 1. Okay. Which means all we are left with is, what is the limit as x approaches infinity of -1 going to be? What's my final answer?
Is -1.
-1. That's it. All right. Excellent. Another way to look at this limit as well is just to look at the denominator. So if I said the limit as x approaches infinity of 1 over 2 to the x, that becomes 1 over 2 to the infinite power, which is just 1 over infinity. So if your numerator remains a constant number, but your denominator keeps getting increasingly large, then 1 or any constant number over infinity is always going to be what? Equal to what number?
0.
0. So that's just another way to look at it as well. Okay. Any questions on that one? All right. 2, evaluate the limit as x approaches 0 from the left of 1 over x. Okay. So for these type of limits where an exponential base is being raised to another function, such as 1 over x, it's a lot easier to think of the graphs. So 1 over x looks like this. This is the graph of 1 over x. And now all we want to do is analyze this limit for this graph. So this says that the limit is approaching 0 from the left. So if I'm approaching 0 from the left side, where are my y values headed?
Negative infinity.
Down to negative infinity, right? So what we do with that is we'll write the limit as x approaches 0 from the left of e to the 1 over x becomes e to the negative infinity. So another way to rewrite any type of negative exponent is to put this as 1 over e to the infinite power. And just like the example above, if your numerator stays a constant number, but your denominator gets increasingly large, where is this limit headed?
0.
0. That's it. There's our limit. So if you think of the graph, it makes it a lot easier to handle this limit. And if you're like, how do I know what 1 over x looks like? Well, you made the calculus. You should know what all the graphs look like. But even at that, you can use Desmos or use a graphing calculator. Graph that function, right? And that'll help you with these limits a lot. All right.
So if we're doing like our homework or later on like a test,
Mhm.
we don't have to like show the graph, right? It's just understood.
Well, if you're proving this by graph, like I'm writing, like say if this question was on a test, I would want to see all of this.
Okay, gotcha.
Yeah. So give me, if you're doing a test, give me all the work you're using. Because if you have an answer and there's no work to support it, then I'm going to wonder how you got it.
Okay.
So show everything that you're doing. I can skip steps because I'm allowed to. You guys, you can't. You skip steps, I assume you're cheating. Show me.
Okay.
Show
So
me.
we could just
all
show
your
like
work.
the general graph. We don't have to put like points though, right?
Exactly. Like
Okay.
I have just the general graph here. I've graphed no points. I've just made a sketch of the function. So, like I said, whatever, like say if this question's on the test, whatever I've written here, that's exactly what I would want you to write for the test.
Gotcha.
Yeah. So if you guys are ever wondering, like, how do I show work? Look at the notes. If I'm showing every step, that's what I want you guys to do. Don't leave anything out. Don't leave anything out for questioning. Okay. Okay. So using our limit laws again, let's go ahead and try these ones out. So this says the limit as x approaches infinity of e to the 2x over e to the 2x plus 1. Well, since we dealt with infinite limits on the last section, we get to use the same tricks on this section. So for this limit, we're going to use the power trick, which means we're going to divide everything by the highest power in the denominator. So what am I going to divide everything by?
2x.
Good. Well, more of e to the 2x, right? But you got it. So I'm just going to divide everything by e to the 2x. Because again, this is a rational function, and limits at infinity look for horizontal asymptotes, right? This is why we get to use this power trick. And now we'll reduce, and I'll get 1 over 1 plus 1 over e to the 2x. And just like the other examples we've seen today, where is 1 over e to the 2x going?
0.
0. Because once again, your numerator is a constant number, but the denominator is getting larger and larger and larger. So it becomes 1 over infinity, which goes to 0, which means all we're left with is the limit. Oops, different color. Is the limit as x approaches infinity of 1 over 1, which just gives us 1. Okay. Any questions on that one? Okay. So once again, for number 4, using the limit properties on the first page, we have the limit as x approaches infinity of 1.001 to the x. Now this is an exponential function, and our base, well, is this base bigger than 1?
Yes.
Yes, right? This base is bigger than 1. So if we have the limit as x approaches infinity of 1.001 to the x, where is this limit headed?
Infinity.
Infinity.
That's it, infinity. Good stuff, right? Because for this one, your graph would look like that, right? And as x headed towards infinity, y would be heading towards infinity. All right. Next one. 5. The limit as x approaches infinity of e to the negative x squared. So this is like the second example we did. So we're going to want to think of this function, negative x squared. And if I graph negative x squared, what type of graph does that make?
A parabola going down.
Good. So this is what negative x squared looks like. This is negative x squared. And what we're saying is that as x goes to infinity, where are your y values going?
Negative infinity.
There you go. Negative infinity. So as x goes to infinity, y is going to negative infinity. And this means that when we rewrite this limit, you'll just get e, oops, you'll just get e to the negative infinity, which again becomes 1 over e to the infinite power, which will become what?
0.
0. I mean, we could have even seen this one without the graph too. We could have rewritten this one as the limit as x approaches infinity of 1 over e to the x squared. And now, if x is approaching infinity, this means you'd get 1 over e to the infinite power, because your denominator is getting larger and larger and larger. And again, it's going to head towards what number?
0.
0. Everybody good with that? All right. And number 6 is just like the one above. We get to power trick this one again. So 6 says the limit as x approaches infinity of e to the 3x minus e to the negative 3x over e to the 3x plus e to the negative 3x. We get to power trick by dividing everything by the highest power below. And I'm sure you see it. You're going to divide everything by e to the 3x. So we just power trick this one again. And this will give me the limit as x approaches infinity of 1 minus 1 over e to the 6x over 1 plus 1 over e to the 6x. Remember, when you have the same base over each other, you subtract your exponents. So negative 3x minus negative 3x gives me negative 6x, which I can rewrite as 1 over e to the 6x. And then by our limit properties, where are 1 over e to the 6 going? What number are these headed to?
Zero.
0. 0. And all that we're left with is the limit as x approaches infinity of 1 over 1, which gives me 1. Yeehaw, y'all. And those are exponential limits. Any questions on that page? Okay. So those are exponential limits. And now we get into 3.2. Look, we made it already. We have the limit laws of logarithms. So if the base of a log is greater than 1, then the limit as x approaches infinity of log base a of x will head towards infinity. And if the base is greater than 1, then the limit as x approaches 0 from the right of log base a of x will head towards negative infinity. As you see by the graphs below, this goes for the natural log and the log function. So if you approach 0 from the left, you see that your y values are headed towards negative infinity. That's why our limit, sorry, not from the left, from the right. From the right, you see that your y values are headed towards negative infinity. And then if your x values are headed towards infinity, then your y values are also headed towards infinity. There we go. Okay. And again, these go for natural logs as well. So maybe I could write that in. Why not? So we can also say the limit as x approaches infinity of the natural log of x will be infinity. And the limit as x approaches 0 from the right of the natural log of x will head towards negative infinity. Okay, cool. So those are our limit laws for logarithms. So let's go ahead and try them out below. So number 1, the limit as x approaches 0 of log base 10 of tangent x. So once again, these are just like exponentials. We have the log of a function. So what we want to do is just focus on the function inside and then apply that limit to the inside function. So we'll go from there. So first off, we want to know what the graph of tangent looks like. And remember, tangent, you have, I'll just draw one piece of it, negative pi over 2 to pi over 2, and tangent looks like this. Okay, of course I can make it prettier because you have vertical asymptotes there and there, but you guys knew that, right? Okay. So what we're saying is that as you approach 0 from both sides on this tangent function, so as you approach 0 from the left and as you approach 0 from the right, tangent is getting close to what number?
0.
0, right? Because the tangent of 0 is 0. So what we say with this is, in order to rewrite this, we're going to say the limit as x approaches 0 of the log base 10 of tangent x becomes the log base 10 of 0 from the right. Now there's a reason for this, because one of them is, can you take the log of 0?
No.
No, right? The log of 0 will always give you an error. And the reason I'm writing 0 from the right is based on our log graphs of above. Can you actually pass 0 on the log function?
No.
So what we're going to do here, so the reason for 0 from the right, because if you ever approach the log or natural log function from the right, y is always going to head towards what number?
Negative infinity.
Negative infinity. So when I say the log of 0 from the right, your answer is going to be negative infinity. That's it. So that's the reason for the 0 from the right. And this will equal negative infinity. That's it again. Think of the graph, but now when you deal with logs, don't just put a 0 in there, put 0 from the right, because now if you're doing the log of 0 from the right, we know that it's always going to head towards negative infinity no matter what. All right. Any questions on that? Good old logs, right? Okay. 2, the natural log of x squared minus 9 as x approaches 3 from the right. So again, like the above, think of the inside function first. What is the behavior of the inside function as x is approaching a number? So I'll draw x squared minus 9, and x squared minus 9 is going to be the graph of what?
So we're graphing x squared minus 9, right?
Yep.
So it'd be a parabola going up, shifted to the
What will
left.
my, well, not shifted to the left. What are my x-intercepts for x squared minus 9?
3 and negative 3.
There you go. 3 and negative 3. So my graph
Shifted down.
looks like this, right? This is the graph of x squared minus 9. And now let's look at what the limit is asking. The limit says, what is the limit as x approaches 3 from the right? So we are approaching this number from the right side. So as x approaches 3 from the right, y is getting closer and closer to what number?
3.
That would be next value. We're close though. So remember, if 3 is an x-intercept, if you have an x-intercept, y must be what value?
0.
0. Y is approaching 0. So as x approaches 3 from the right, y is approaching 0. Make that a little prettier, right? Y approaches 0. Which means if we come back to our log, I would say the limit as x approaches 3 from the right of the natural log of x squared minus 1 becomes the natural log of 0. But we can't take the natural log of 0, so we have to say the natural log of 0 from the what?
From the right.
From the right. And based on the natural log and the log, if you ever approach 0 from the right, where is your limit headed?
Nearly infinity.
Negative infinity. That's it. All right. Any questions on those two? Know the graph, know how to apply your limit laws. And this stuff is easy. Okay. 3. The limit as x approaches 2 from the left of log base 5 of 8x minus x to the 4th. So once again, think of the inside function. Let's go ahead and graph that. 8x minus x to the 4th. Here, I'll write it out here. Well, if we wanted to graph this, the easiest way to graph a sketch of this would be to think of the x-intercepts. So what could I factor out of this function?
X.
An
X to the fourth.
x. And that would leave me with x times 8 minus x cubed. So based on this, where would I have x-intercepts at? I can't even draw that right. Huh.
Is it 0 and 2?
0 and 2. Good. 0 and 2. So I would have one at 0. And then I would have one at 2. Okay. And now 8x minus x to the 4th. I guess you have to think a little bit about the characteristics of a polynomial function. If this is x to the 4th, which way is it going to open? Up or down?
Is it up?
So remember that if you have a positive x squared or any even degree, your tails will always open up. But if you put a negative in front, your tails will always open
It's a negative.
down, because that's a negative x to the 4th, right? Which means my function would just look something like this. Probably just ugly like this. There you go. There's your sketch. Okay. And now we have to think about what the limit is asking us. 2 from the left. Oops, I erased everything. There we go. So if you approach 2 from the left, your y value is getting closer and closer to what number again?
0.
0. Which means coming back to the limit, I would say the limit as x approaches 2 from the left of log base 5 of 8x minus x to the 4th becomes log base 5 of 0. But can we use 0?
No.
No, we have to say 0 from the right. And where's this limit going?
Negative infinity.
Negative infinity. That's it. Okay. Once again, thinking of the graph is the easiest way to handle these limits. What number is the inside function getting close to? And that'll tell you what your log is going to get close to. So, any questions on that? Oh man, it's a rough Monday, right?
Yeah.
Recovering from the Super Bowl.
Oh man. Super Bowl. Okay. Number 4. The limit as x approaches 0 of the natural log of the cosine of x. So again, just like all the other problems, think of the inside function. So cosine, when you graph it, it goes through 0 or 1?
1.
1, right? So there's 1. So cosine would look something like this, right? So this means that we have graphed the inside function, and now we want to apply the limit to the inside function. And this says, as you approach 0 from both sides, y is getting closer to what number?
0.
Y.
1.
1, right?
Oh,
Y
yeah.
gets closer to 1 when you approach 0 from both sides. So this means that for this limit, we would get the limit as x approaches 0 of the natural log of cosine of x. And we see that the inside function as x gets closer to 0, will become 1. So this just becomes the natural log of 1. And does anybody know what the natural log of 1 is?
0.
0. Such simple answers, right? Okay, cool. And then for the next one, we have sine. So once again, think of the inside function, sine of x. Graph the sine function. And we know that sine looks like this, right? It'll go through 0. So now, once you graph your function, you apply your limit. We are approaching 0 from the right. So as x approaches 0 from the right, y is getting closer to what number?
0.
0. Good. Y gets closer to 0. So again, we would write the limit as x approaches 0 from the right of the natural log of sine of x would become the natural log of 0. But can we use 0?
No.
No. So we say 0 from the right, and this limit's headed towards what number?
Negative infinity.
Negative infinity. There we go. All right. Cool. All right. 6. The limit as x approaches infinity of the natural log of 1 plus x squared minus the natural log of 1 plus x. So before we apply this limit, we have to go back and remember our log properties. What I want to do for this problem is combine these two logs into one. So we see that these are connected by subtraction. So what would be another way to rewrite this?
Division.
Good. So you would get the limit of the natural log of what?
Is it 1 plus x squared over 1 plus x?
That's it. 1 plus x squared over 1 plus x. Because this uses the log property. If I said the natural log of x over y, I can rewrite it as the natural log of x minus the natural log of y. And I could rewrite it the other way. So what we did was we took the natural log of x minus the natural log of y and rewrote it as a fraction again. So we just reversed the process. Okay. And now we have the natural log of 1 plus x squared over 1 plus x. And what we're going to do next is take this limit and apply it to the inside. So we'll get the natural log of the limit as x approaches infinity of 1 plus x squared over 1 plus x. And now we have the limit of this rational function, which means we get to power trick it. So I'm going to divide everything by what?
By x.
By x. And you get the natural log of the limit as x approaches infinity of 1 over x plus x squared over x over 1 over x plus x over x. Simplify. I got room there. Equal to the natural log of the limit as x approaches infinity of 1 over x plus x over 1 over x plus 1. Okay. And now let's go ahead and apply the limit to these two terms. If x approaches infinity, where are 1 over x headed?
0.
0. So this would become 0, and then that would become 0. And what we get left with is the natural log of the limit as x approaches infinity of x over 1. And now, if you plug in infinity, you'll get the natural log of infinity, which is just going towards where?
To infinity.
To infinity. That's it. Good. Any questions on that one? Not bad. Okay. 7. Same situation here. The limit as x approaches infinity of the natural log of 2 plus x minus the natural log of 1 plus x. So now we want to combine these into one log. So we're going to use that same rule from above. So I'll have the limit as x is approaching infinity of the natural log of 2 plus x over 1 plus x. And then apply the limit inside. Oops, that's not inside. Too many L's. The natural log of the limit as x approaches infinity of 2 plus x over 1 plus x. And then, again, we get to power trick this. So we'll divide everything by what?
X.
X. So you get the limit as x approaches infinity of 2 over x plus x over x over 1 plus 1 over x plus x over x. Simplify. And we get the limit as x approaches infinity of 2 over x plus 1 over 1 over x plus 1. All right. And then we know that 2 over x and 1 over x are headed towards what number?
0.
0. And all we're left with is the natural log of the limit as x approaches infinity of 1 over 1, which just becomes the natural log of 1, which means our answer is
0.
0. Oh my goodness. All that fun time for that little answer. And those are logarithmic limits. Logarithmic limits, exponential limits, and guess what? We're done. Short lesson. So if you have questions over it, please ask. If you have questions over homework, ask away. We have a lot of time left.